right, thank you. All right, good morning, everyone. So let's continue the discussion from yesterday. So for now, we're still looking at the Ising Hamiltonian, but I promise later on this lecture, we will talk about more general Hamiltonians. Now, so yesterday we talked about the transverse field Ising Hamiltonian with a coupling constant G. And if you set G to be 1, well, for any G, you have a Z2 on-side symmetry, eta squared is 1. You also have a translation symmetry, which just brings any operator at side J to side J plus 1. At G equals to 1, you have an enhanced symmetry, which we call D, meaning that at G equals to 1, D commutes with the Hamiltonian. And yesterday, I wrote down this expression out of thin air, and today we will continue the derivation of this operator D. And these three operators at G equals to 1 give a very interesting algebra. In particular, D squared is 1 plus eta times T, which in particular is not a group-like multiplication law. As you take the L goes to infinity limit, you are approaching the continuum CFT. In that limit, the lattice translation by one side becomes a trivial operator, meaning that T becomes 1. And then we recover the non-invertible algebra of the Ising conformal field theory, which I think Yifan will talk about in his lectures.
Yeah. This one part is over to the projection.
Yes.
So you could study this within this symmetric subspace. In that case, if you remove 2, then T squared can be 1.
Oh, absolutely. Yes.
Inside the projector subspace.
That's right.
It looks like this square 2 is this normalization factor somehow is putting by hand. You know?
Oh, very good. So there are two comments in your questions, right? So first is that it contains a unitary part, UKW. And in the eta equals to plus 1 sector, UKW squares to 1, and it's just an ordinary unitary operator. Great. And in the eta equals to plus 1 sector, it's a symmetry. The second comment, and that's totally correct, but in the entire Hilbert space of 2 to the L dimensional Hilbert space, we need a projection to make it a symmetry. The second comment is about the root 2. Indeed, at this point, the root 2 seems completely unjustified. In fact, I could have gotten rid of this root 2. And it's not just I could have. In fact, in our paper from last year, we didn't put a root 2 factor. It was only later on we found it more natural to put a factor of root 2. But yeah, indeed, we can drop the root 2, and that wouldn't affect any of the thing I'm going to say. One thing it will affect is that it will introduce a factor of 1/2 here. But I mean, we're just talking about operators, right? If you have a conserved operator D, multiply it by 7 or divide it by 17, that's still a conserved operator. You don't care. So the complete honest answer is that on the lattice, I don't really have a good justification for the factor of root 2. You can say that the reason I put a root 2 is only because I want to match the normalization in the continuum CFT. And in the continuum CFT, as Yifan will discuss, there is a preferred normalization for every conserved operator. Now, later on, I will provide, perhaps it's just more of an aesthetic reason why the root 2 is good. But yeah, I'll get to that point. Yeah. Any other question from yesterday? Okay, if not, let's continue. So to derive the non-invertible symmetry, we took a detour to talk about two different models, which are about Majorana fermions. So we call them the Majorana-Chen models. We consider two Hamiltonians. Each one of them consists only of nearest neighbor interaction between the Majorana fermions. There's a plus and minus difference. When you choose the plus sign, that corresponds to the fermions with a periodic boundary condition. When you choose the minus sign, that corresponds to fermions with the anti-periodic boundary condition. And you can think about the relation between H plus and H minus as inserting a defect corresponding to -1 to the F at the link between 2L and 1. But that's just a fancy way of describing choosing different boundary conditions in Hamiltonian lattice models. For for both of H plus and H minus, you have a fermion parity symmetry, -1 to the F, which just flips the sign of the fermion everywhere. You also have a Majorana translation symmetry. For the plus problem, it's obvious. You can shift chi L to chi L plus 1. That leaves the Hamiltonian invariant. For the one with the anti-periodic boundary condition, with a little more thought, you'll see that there's still a lattice translation symmetry. You just have to flip one sign towards the end. And the continuum limit of the Majorana lattice model is that it goes to the free Majorana CFT with 0 mass. So you have a left-moving Majorana vial fermion and a right-moving Majorana vial fermion. This CFT has 2 Z2 symmetry. You can choose them to be generated by a fermion parity, which flips the sign of both the left-moving and the right-moving component, or and another generator which only flips the sign of the left-moving component. So if you compare the two, the lattice model and its continuum limit, the -1 to the F just match on the nose. There's no problem with that. The chiral fermion parity is more subtle, and this is common when we talk about lattice fermions. It is very common that the chiral symmetry of the continuum fermion theory usually emerges or emanates from some more subtle symmetries on the lattice. In this case, it's the Majorana translation symmetry that becomes the chiral fermion parity in the continuum. I probably won't have time to say why this is the case, but the model is quadratic, so you can solve it exactly, look at the spectrum, and you can identify how the translation symmetry acts and compare that with the chiral fermion parity action. Okay. All right. Now, yesterday we also talked about the algebra of the fermion problem. And in particular, we find that for the periodic boundary condition, T plus and -1 to the F anti-commute. And this -1 will be very important down the road. Whereas if you consider the anti-periodic problem, they commute. And this signals an anomaly of this Z2 cross Z2 symmetry of the continuum CFT. But it's a very elementary fact you can derive on the lattice, as we did yesterday. Good. All right. So I'll keep it here. So it's an anomaly. But it's an anomaly of the Majorana system. Okay. All right. So moving on, we eventually want to get back to the Ising model. So we want to relate the Majorana fermion to the Ising lattice model. To that end, we perform the Jordan-Wigner transformation, where we did the following change of variables. Make sure I get the Y and Z straight. No, I got it backwards. Okay, so we replace the local fermion variables by some Pauli operators. And under this change of variables, the same Hamiltonian becomes all right, so this is where we stopped yesterday. Yes?
Is it obvious why you said that indicates an anomaly?
Sorry, what was the question again?
Is it obvious how that indicates that there is an anomaly?
Okay, so the question was, is it obvious that this indicates an anomaly? First, it depends on what you would mean by anomaly. But here is just for ordinary invertible symmetries. So by anomaly, I meant it could be, it presents an obstruction to gauging that very symmetry. And the fact that there's a projective algebra means that you cannot find a state that's simultaneously invariant under both symmetries. And that will signal an anomaly in the continuum context. However, here we're on the lattice, and one of the symmetry is the lattice translation. It's not clear how you will gauge the lattice translation symmetry. So a better way to characterize the anomaly is that this presents an obstruction to a trivial phase, a phase where you only have one ground state and an older one gap. And since that you have a projective algebra with that minus sign, this means that your spectrum has to be at least doubly degenerate. So it cannot be a trivial phase with a unique ground state. So it's in that sense we call it an anomaly on the lattice. But it flows to an honest-to-God anomaly of invertible symmetries in the continuum CFT for that Z2 cross Z2. But on the lattice, to phrase it as an obstruction to gauging is more subtle because it involves a lattice translation.
The second relation does not indicate any anomaly, T minus.
Good. So I think your question is that, does that mean we only have the anomaly for T plus but not for T minus? Yeah. So I hate to give answers like yes and no, but this time I'm going to say yes and no. Yes, in the sense that the minus sign is only in T plus, but no, in the sense that you should really think about T plus and T minus as one symmetry, but with different boundary conditions. So when I say there's an anomaly, it really refers to the symmetry without having specified the boundary condition. And what I meant by anomaly is that there exists a boundary condition where you see such a projective sign. Okay. All right, so last time we did this change of variables and rewrote the fermion Hamiltonians in this form, which is almost like the transverse field Ising model at g equals to 1, except for the very last term. You might also notice that there I use capital Xj and capital Zj for the Pauli operator. Here I use sigmas. So it seems that I'm being inconsistent with my notations. But actually they are not exactly identical, as we will see later, but the difference is not terribly important. So we're not done yet. You know, we made a mistake in one link, and today we would like to fix that. And to fix that, there are basically two equivalent ways to do it. One way is that we should interpret, well, first of all, we learned that Majorana, the Ising model, is not globally the same as the Majorana fermion model. And one way to really relate them is to think of Ising as Majorana fermion with the -1 to the F symmetry gauge. And gauging generally changes the model. But I'm not going to follow this route for the following lecture. I'm just going to present to you the procedure that comes out of gauging. And this procedure should look familiar for people who have studied bosonization in continuum field theory or for people who have studied string theory, worksheet string theory. Okay, so let me describe the procedure that would relate the Majorana fermion to the Ising model. Now it consists of two steps. In the first steps, we would like to add the model with the periodic boundary condition and the anti-periodic boundary condition together. So we have two L fermions. So each, let me take two copies of the Hilbert space. So here, H plus minus. Each one of them is a 2 to the L dimensional Hilbert space. I use H minus to stand for the Hilbert space for the anti-periodic problem, and similarly for H plus. They're really isomorphic. I just add the subscripts to make it clear. But if you don't like the subscript, you know, just ignore it. So I take the direct sum of the two Hilbert spaces, and therefore, and to obtain a bigger Hilbert space, which is temporarily 2 to the L plus 1 dimensional. And on this bigger Hilbert space, I consider a big Hamiltonian, where I put the anti-periodic Hamiltonian in this block, and periodic boundary Hamiltonian in the lower block. Okay? So I enlarge the system. You can think about it as adding a qubit to the system. Now this might look ad hoc, but for people who have studied string theory, this is actually what we do in the first step of GSO projection, where we include the NSNS and RR sector together. To be more precise, this is more like type 0, doing the GSO projection for type 0 superstring, type 0 string.
So are we in the Ising or Majorana?
Sorry, say again?
Are we in the Ising or in Majorana?
Good. So we start from the Majorana. So we take the Hamiltonians, the anti-periodic, this H minus is for the Majorana. So we use the ingredients from the Majorana problem to build this intermediate Hamiltonians H tilde, which acts on an intermediate bigger Hilbert space. Okay? It will become clear why we do that in just a moment.
H plus minus this one.
Oh, H plus.
H plus and H minus that we have there.
Yes, yes, it's the same H plus and same H minus over there. That's right, that's right. Okay, so in the first step, we include both both boundary conditions. And there's a second step where we do the projection. So the projection we would like to do is to set -1 to the f to be +1 in H minus, -1 to the f to be -1 in H plus. Okay? Now, why do we want to do that? So let's take a look at this Hamiltonian where we have a mistake in one of the link. If we were in the H minus block over here, that means we are choosing the minus sign here, right? So that corresponds to minus. These two minus are correlated. But in this sector, you would like to project to the +1 eigenstate of -1 to the f, so that this entire factor is a minus sign. If this entire factor were a minus sign, that's the same as the rest of them, and we retrieve the Ising model Hamiltonian we started with. Okay. On the other hand, if you are in the lower right block with the periodic boundary condition, you would like to choose -1 to the f equals -1. So if we are in H plus, we have the plus sign here, but then I would like to restrict to the -1 eigensector so that this entire factor is -1 again. And I have the same sign as the rest of the term. Okay? Good. Okay, so after these two steps, you find that the Hamiltonian, okay, there's one more thing. So I do a projection. So I define a new Hilbert space to be this bigger one subject to the projection. So let's take a look at what we have done. We started with the Majorana problem, which could be either with the periodic boundary condition or the anti-periodic boundary condition. Each one of them exists in a 2 to the L dimensional Hilbert space. In step number 1, I temporarily enlarge the Hilbert space by a factor of 2. In the string theory language, that's taking the union of the NSNS and RR sector. In the lattice perspective, it corresponds to adding a single qubit to the lattice system. In the second step, I do a projection with respect to one of the Z2 symmetry. So in the first step, I make the Hilbert space twice as large. In the second step, I make it half as small. So in the end, the final Hilbert space, subject to the projection, is 2 to the L dimensional. And it's not a coincidence I use the same symbol as the Hilbert space for the original transverse field Ising model we started with.
Is this one tensor product Hilbert space?
Very good, yeah. So at the end of the day, it is. But from the construction, it's not entirely clear why it is. In fact, from the very beginning of the fermion problem, it's not even clear why that, what we mean by a tensor product Hilbert space. Do we mean with respect to one Majorana site or two Majorana site? So I didn't define the notion of tensor product Hilbert space when I started with the Majorana problem. But the final answer is, since we get back to the transverse field Ising model, it is on a tensor product Hilbert space. Now you could have questioned that maybe, is it a coincidence, is it a miracle that I land on a tensor product Hilbert space? But I think the right way to explain it is that we're doing gauging here. And gauging a Z2 symmetry, you can always solve the Gauss law, so that final Hilbert space is a tensor product Hilbert space. Okay, so after these two steps, we basically replace this factor uniformly by -1. And we retrieve the transverse field Ising model. Let me just write quickly the relation between. So in the end, this capital Xj is sigma Jx, sigma Jx. Right, remember sigma Jx lives in only one of the block, and Zj. All right. Okay, so this clarifies the relations between the Majorana fermion and the Ising model. But why do we do this? The reason we did this is because we want to track the symmetries of the Majorana problem to the symmetries of the Ising problem. And in particular, let's ask the question, what happens to the Majorana translation when you go through this lattice bosonization? You see, T plus, the symmetry for the periodic boundary condition, it's a Z2L symmetry because I have 2L Majorana sites. However, in the Ising model, that T over there is only a ZL symmetry because I only have L site for the Ising problem. So what happens to that Majorana translation? Okay, well, to do that, we have to follow what happens to that operator through this two-step process. So naively, I can define an operator, which I call T tilde. Everything that comes with a tilde acts on that intermediate bigger Hilbert space. So this T tilde I define to be T minus here and T plus here. Okay, so I use the Majorana translation operator for the anti-periodic boundary condition here, and the Majorana translation for the periodic boundary condition here. Okay, this is a good operator acting on this big Hilbert space H tilde. But so this is okay in the first step. But in the second step, we would like to do the projection. And that's where we ran into an issue. So that's where this minus sign becomes important. When we try to do the projection, we see that T plus does not act within this projected Hilbert space. Right? We did a projection to a definite -1 to the F eigensector. However, T plus does not commute with the Z2 symmetry with respect to which you did the projection. So this operator would take you outside that projected Hilbert space. So it does not act on H. Okay, is that clear to everyone? Right, you did a projection, you have an operator that doesn't commute with the projection operator, and therefore this operator doesn't act within the projected Hilbert space. Okay, but that's good news, because that explains why the Majorana translation symmetry doesn't just become an invertible symmetry in the Ising model. Instead, you can consider the square of this operator. The moment you square it, that minus sign disappears. So this operator does act on the projected Hilbert space. So I can define T to be the square of the Majorana translation restricted to the projected Hilbert space. And it's, again, not a coincidence. I'm using the same notation, T, as the Ising translation over there. And this is the meaning why we usually say twice the Majorana translation is doing Ising translation by a single site. And we could have stopped the story here. We explain why the Majorana translation disappear as you do the lattice bosonization. We also explain why doing two sites Majorana translation corresponds to one Ising translation. But if you think about it for a little bit, we are being a little bit too cruel to the symmetries here. It's only T plus that has the minus sign issue that forbids T tilde being an operator or being a symmetry of the final Ising model. But T minus is completely innocent, right? T minus commute with minus 1 to the f. So we shouldn't punish T minus for the sign he didn't commit. So instead of considering this operator, what if we define this operator? So I put a root 2 here, again for just normalization reason. And I put the innocent T minus in this block. There's nothing wrong with it. But then in the lower right block, I just put a 0. Okay. Now this operator commutes with the projection. So it can be restricted to that projected Hilbert space. And therefore, it's a symmetry of the Ising Hamiltonian. And again, I use the same symbol D as the one we talked about yesterday, because it's a straightforward calculation to check that they are the same. Well, I should say that here I didn't provide the explicit expression of T minus for you, but it can be written very explicitly in terms of the fermion operator, chi. And then you can do the Jordan-Wigner transformation there to rewrite T minus in terms of the Pauli operators. And then you will see that it agrees with the expression on the upper left corner. Yeah, Yifan.
So depending on the definition of T plus and T minus, I guess you can swap the signs around?
Which sign?
The signs in your equation that characterize the analogy.
But what do you want to change? You want to change the definition or
no,
change
whether it's the T minus that remains innocent in the end or T plus. Your definition of T plus and T minus.
No, but I think you always have to, it's always the T minus that survive. T plus, maybe another way to ask your question is that we now have explained what T minus mean in the Ising model. What does T plus mean in the Ising model? Does it have a meaning in the Ising model? It has a very nice meaning in the Majorana model, but what about in the Ising model? So I'm not going to talk about that in the lecture, but let me give Yifan a quick answer. So it corresponds to a map from the untwisted Ising model to the Ising model with a Z2 twist. So it corresponds to one of our lasso action. But it's not an operator acting within the untwisted Hilbert space.
That's a question. So here, this is an example where non-invertible symmetry is promoted to invertible symmetry by extending the Hilbert space. Right? So the question, natural question is then how general is it? Is there a general guarantee? It's somewhat like a purification of the...
Yeah. Well, your colleague just wrote a paper.
That's
right. So as shown in that paper, in 1 plus 1D CFT or in 1 plus 1D system, every non-invertible symmetry can be made invertible the moment you include all the defect Hilbert space.
Yeah. Then the second question is then, in that context, for example, is the project, well, let's see, is that if you can imitate the whole procedure, can you, and then regard that as a gauging of some sort in that very general context?
Well, let me not answer the question on general context, but for this Kramers-Wannier, indeed, you can interpret it as gauging in the time direction, only in the future. So that's the perspective I'm not offering here, but we discussed that in one of the...
The question was, do you expect that to be hold in general for general non-invertible?
For general non-invertible symmetry, I don't think that's the case. At least it won't correspond to gauging an invertible symmetry, let me put it that way.
Oh, okay. I see.
Right, the Kramers-Wannier is very specific because it corresponds to gauging that Z2 symmetry. But generally, you might not even have an invertible symmetry to talk about. Oh, Max, yes.
Maybe I'll ask about this, the projection. So usually, when we gauge Z2, right, with some of the spin structures, so we have. So I know that this is right, but I'm still puzzled why it's in one sector you project into -1 to the f equal +1, and in the other on -1.
Okay, good. So in the continuum, there's essentially no difference. Well, let me just quickly answer. There's no difference between the two. I could have chosen +1 for both sectors. But then you would say, wait, if I had done that, the Hamiltonian doesn't look like transverse field Ising anymore. Right? So it doesn't seem that I arrive at the right answer. But actually, you can show that if you choose both signs to be plus, what you arrive is the Ising model with the Z2 eta symmetry gauged. Another way to say it is that, as you know very well, choosing the sign, if you flip the sign of -1 to the f in the RR sector, that will give you two different bosonic systems, and those two different bosonic systems are related by gauging.
And how, but in one case you maybe land on something with a twist defect in the Ising?
No, in both cases you land on the Ising by itself. Yes. It's not totally obvious, but it follows from the ordinary gauging procedure. I choose the minus sign because it looks nicer to do it on the blackboard. But you could have chosen the plus sign, and with just a few lines of algebra, you can show that it's the Ising coupled to a Z2 gauge field. It's kind of a coincidence here that Ising and Ising mod Z2 are the same on the lattice, so you couldn't tell the difference. But the moment you do it for two Majorana, it gets interesting. For one sign, you get the Levin-Gu. For the other sign, you get the XY model. Yes.
Just to follow up on the previous question, for the non-experts, could you specify what the paper was that you referenced?
The paper I referenced, for what part of the discussion? The gate. I'm sorry, yeah.
You didn't say.
I didn't say because I embarrassingly forgot the name of one of the authors. So I didn't. Okada, thank you. So it was by Tachikawa and Okada, yes. Yeah. Any other questions? Okay, great. Right, so we find an operator D that commutes with the Ising Hamiltonian and acts on the same Hilbert space as the Ising model. But the price we pay is that it has a big kernel, as you can see manifestly from here. There's a big zero here. So it's not an invertible symmetry. And in fact, from this characterization, from this perspective, it's clear what D square is. When you take D square, you get T minus square here. But that's just the Ising translation projected to one of its block. So it's just the Ising translation T times 1 plus eta. So that gives a very straightforward derivation for the algebra D square over there. You see, the beauty of it is that if you look at that expression of D up there, it's actually not totally straightforward well, it is straightforward, but it's not totally obvious why D squared gives you that expression. But from the bosonization picture, this relation follows immediately. Okay, good. Is there anything else I want to say about this point? Yes.
When you put T plus to be, when you replace T plus with 0, is it still a symmetry of this doubled system? So H minus plus H plus system?
Yes, because what do we mean by a symmetry? Well, first of all, it's stronger than that.
It's still okay.
Yeah. Even T tilde is a symmetry of the double system. But that's not our goal. Our goal is to find the symmetry of the Ising model, which is the projected system. So I want to make sure it survives the projection. T tilde does not survive the projection. T tilde squared survives the projection. D also survives the projection. So that's why it becomes a symmetry of the projected problem. Okay, good. All right, now I want to, where do I want to do it? Let me do it here. So before I move on to some application of this non-invertible symmetry, well, let me first conclude one thing. So here what we have seen is that an invertible symmetry, namely the Majorana translation of the Majorana problem, becomes a non-invertible symmetry of the Ising model. And this is something that happens repeatedly in this context, that an invertible symmetry with an anomaly becomes a non-invertible symmetry after gauging. not every non-invertible symmetry arises this way, but a large class of them do, including the non-invertible chiral symmetry in QED. So that's one general lesson that's worthwhile noting. Okay. All right, so now before I move on to the application part, I want to present another expression for this operator D. And this is somewhat related to various questions that were asked today and yesterday. In fact, I think there are at least 5 or 6 different presentations for this operator D. So it's not very helpful to present all of them. This is one of them, written in terms of a sequential quantum circuit times a projection. This expression has several advantages, but it also has some disadvantages. One disadvantage of this expression is that it doesn't make the translational invariance manifest. Right, so as I emphasized, D commutes with T. And that is obvious from this expression. T is made out of T minus and T plus. And D is also made out of T minus, so dt equals Td. But that's not manifest the way I wrote it here. I chose an arbitrary point to start my product. But somehow the claim is that after multiplying the projection, it is a translationally invariant operator. So now I'm going to present a different expression for the operator that makes translation symmetry manifest. And this is known as the matrix product operator. So some of you might be familiar with matrix product states, but this is just a simple operator generalization of that. So the claim is that this operator is a non-trivial calculation, but it can be done, can be written in this way. Okay, so I have to define the ingredient here. This U, this blackboard font UJ, is this. Okay, so let me remind you that 0 and 1 are the eigenbases for the Pauli Z operator. Plus and minus are the eigenbases for the Pauli X operators. This is a cat state. This is a bra. Both the cat and the bra are on the site J. Okay, I should have written a J here, but just to simplify the notation, I only write J once. Okay, so what does this mean? So this is an operator acting on size J. I group 4 such operator into a 2x2 matrix. And so this is an operator value matrix. And then I multiply then by the 2x2 matrix multiplication in this expression, and then take the trace in that 2-dimensional virtual space. So this 2-dimensional space, which I create by this 2x2 matrix, is usually called the virtual space or the bound space. And here we have the bound space is 2-dimensional. So let me just write it here. The bound dimension is 2. Okay. So this operator can be schematically written in this way. So the vertical legs are the physical legs. So this is an operator acting on a 2 to the L dimensional Hilbert space, should have L legs coming from the past, and it should have L legs going to the future. So those are these legs. But then in addition, so that's the final output of this operator. But in the intermediate step, it can be written as as some contraction of this virtual space legs. So this horizontal leg is the bound dimension, bound space leg. And we are multiplying the matrices together, so we are connecting them horizontally. This little blob here is the U I just defined. You see, this U has several different legs. It has the legs in the physical direction, one bra, one cat. So that's one past leg, one future leg. But the U is also a 2 by 2 matrix. So that's why it has two horizontal legs. We multiply them together, so we connect the horizontal legs in that manner. And then in the end, we take a trace. So this expression makes it clear that this is a translationally invariant operator. It's a somewhat non-trivial calculation to show that this equals that. Okay. So in the I wrote a few exercise problems where you can play with this expression. Using this expression, you can show the desired properties like d xj is zj plus 1, d, etc. Using this expression, it's also clear if you compute dzj, not zj plus 1, but just dzj, a single factor of z, you cannot write it in that form. Okay. So more generally, many of the non-invertible symmetry in lattice system, not just in 1 plus 1D, but in diverse dimension, take this tensor product, a tensor network operator form. So in higher dimensions, they have a slightly fancier name. They are known as PEPO rather than MPO. But more generally, they are just some tensor network operators. And this expression also makes the notion of locality somewhat clear, right? Because it's not the non-invertible symmetry is not literally a product of unitaries. What would be a product of unitaries, right? So if you have just an on-site symmetry, like eta, it's just this. Right? There's no horizontal legs connecting them. Each factor is just an xj, and it has one leg in the past, one leg in the future. But a non-invertible symmetry cannot possibly be a product of unitary, because a product of unitary is still unitary. This is kind of the closest you can get when you march into the non-invertible world. It's not the product of unitaries, but you have to connect the horizontal legs. I want to also comment on the root 2. Take this expression. What's the freedom in redefining this operator? And let's look at this expression. You might think you have the freedom of rescaling the blackboard uj by some factor. Maybe I can put a 7 here. But if I had done that, I would get a 7 to the lth in my final operator d, because this is like a local factor. It's not natural from the MPO point of view to rescale your operator just by a single factor of 7 or root 2. And the claim is that you have to put the root 2 here for this expression to literally agree with that. So somehow the MPO, the matrix product operator expression, knows about this root 2. I don't have any further deep insight about this. Well, I don't have any deep insight about why this works, but the root 2 is secretly there.
Yes. So I guess it's not really manifest in this thing, the fact that it's kind of sequential or not even finite depth or anything.
Yeah, thank you for the question. Yeah, so there are like 5 or 6 different presentations for the operator D. Each one of them has its own advantage. The advantage of the MPO presentation is that it makes translation symmetry manifest. However, it doesn't make the fact that it doesn't make the depth manifest. It also doesn't make the fact that it contains a projection manifest. But it's actually building, and you can actually show that using techniques from tensor network that it is a projection operator. And this expression, on the other hand, doesn't make translation symmetry manifest, but it does make the fact that it contains a projection manifest. So yeah, that's a very good comment. Thank you for reminding me of that. I wrote it in my notes, but I forgot to say it. Yeah, Diego.
Yes. Are the bond dimensions one dimension related, or?
That's a good question, and the honest answer is I don't really know. Here, the quantum dimension. So, and it's also a little bit subtle because if you want to define a quantum dimension, there's an unambiguous quantum dimension in the continuum. Here we are on the lattice, and because of the mixing with the lattice translation, it gets a little bit murky. Yeah. So the short answer is I don't know, but I think it's probably related. Okay.
Related question. Yeah. So, is there any interpretation of the horizontal legs in the continuum limit?
I think the intuition is that, as you know, the Kramers-Wannier symmetry corresponds to gauging a Z2 symmetry. So the horizontal legs is kind of like the gauge fields in introduce. Yeah.
So it's related to the quantum dimension.
Probably. Yeah.
At least for the ones generated by Hopkins.
Yeah, but I kind of don't want to comment on that because of the mixing with lattice translation, right? Because quantum dimension is √2 in the continuum. It's not 2.
That's the connection in the Hopkins.
Perhaps. I don't know. Okay. All right. Now moving on. All right. So now let me talk about some application. Okay. So suppose someone hands you a local Hamiltonian that enjoys this non-invertible symmetry. What can you say? So the kind of problem that we would like to answer is the phase of a local Hamiltonian. So in particular, we would like to take L to be very large or even to infinity. So let's recall the phase diagram for the transverse field Ising model. So this is the coupling constant G. Here G is 0, here G is 1. And as we discussed last time, when G is very large, right, the XJ term will dominate. And here the Z2, wait, did I get it backwards? Hold on. When G is very large, okay, I got it backwards here. The Z2 is unbroken. So this, in the condensed matter literature, is known as the disorder phase. In this phase, the spectrum of your Hamiltonian looks like this. So you have a unique ground state. If you are in the infinite G limit, this unique ground state is the O plus eigenstate. It's a product state. And then you have an order 1 gap, and then there's something up there. If you are here, then Z2 is broken. You have an order phase. And the spectrum looks like this. You have two very low-lying states, and there are some linear combination. It's important that there are linear combination of this state, where their separation is e to the minus L, some number, and then there are some order 1 gap. But if you are right at the Ising CFT point, G equals to 1, your spectrum will look like this. Where the gap scales like 1 over L. Okay. So this is the phase diagram for the ordinary transverse field Ising model. Right? You have a gap phase here, you have a gap phase there. In this region, you have two low-lying states. Their energy splitting is exponentially small in the volume, in the system size. That signals the spontaneous symmetry breaking of the Z2. Up here, you have a unique ground state, and then there's an order 1 gap. Right at here is a second order phase transition, and the energy splitting shrinks as you take the infinite volume limit, and the rate it shrinks is polynomial in 1 over L. Okay. So the kind of question we would like to ask regarding the non-invertible symmetry is that if the system has a non-invertible symmetry, what can we say about the large L in the of the model in the thermodynamic limit? What does the gap? How does the gap scale? How many ground state you would like you will have? If you only look at this, the ordinary transverse field Ising model, you only have the non-invertible symmetry at g equals to 1. And right at this point, you have a non-trivial spectrum. This is not a trivially gap phase, right? It's a gapless spectrum. This is what we would call the trivially gap phase. It's gap. And saying that it's trivial in 1 plus 1D just means that it has a unique ground state. But at this point, there's something non-trivial. So maybe it's suggestive that the non-invertible symmetries implies the thermodynamic limit of the model is non-trivial. But here you only have one data point, so maybe it's not too convincing. And therefore, you would like to consider a more general model while still preserving the non-invertible symmetry. And there are many such deformations. In fact, there are infinitely many such deformations. One way to see that is if you go back to the Majorana model. You know, we made a big deal that the Majorana model is different from the Ising model. But they only differ globally. And locally, the map between the two models is straightforward. And we know that the non-invertible symmetry, when you map it back to the Majorana model, just corresponds to the Majorana translation. So you can write down infinitely many fermion interactions that preserve the Majorana translation symmetry. And then you can map it back to the Ising model to write it in terms of the spin variables. Here, let me talk about one particular deformation, which will illustrate some general feature of deformation that preserve the non-invertible symmetry. So this example was introduced by O'Brien and Fendley in 2007. Okay. So the Hamiltonian the first part is just the transverse field Ising Hamiltonians. And then there's a second part, which is the interesting deformation they have. So the G deformation, as we discussed, will break the non-invertible symmetry, but it preserves the Z2. When you fix at G equals to 1, then the lambda deformation preserves both the non-invertible symmetry and the Z2. Let's check that. It's really easy. Well, the fact that it preserves Z2 is obvious. It just has to be quadratic in Z. Great. How do you check if something preserves the non-invertible symmetry? Well, you just try to commute your Hamiltonian through D. And what does D do? D maps X to ZZ and ZZ to X. So when you do that, you swap the two terms. And therefore, this deformation preserves the non-invertible symmetry as well. It's a rather minimal deformation, you know, involves 3 sites of the transverse field Ising model. And then you can ask, what's the phase diagram of this model? And that's what O'Brien and Fendley did. So they have some analytic analysis. They also have the DMRG numerical analysis. And the phase diagram looks like this. So let me write it here. The Z2 eta symmetry and the non-invertible symmetry D. So the G deformation preserves this, but break non-invertible symmetry. The lambda deformation preserves both. So when lambda is 0, this phase diagram was already up there. Let me just reproduce it. So in this whole region, you have some disorder phase, some gap disorder phase. In this region, you have an order phase, which is also gap. Now, the interesting thing is when you set G to be 1 and go along the lambda direction, this point we know is Ising conformal field theory. But in fact, there's a whole region where this is the C equals to 1/2 Ising CFT. This is to be expected, because if you start with the Ising conformal field theory point, there's no relevant deformation that preserves both the non-invertible symmetry and the Z2 symmetry. I think Yifan will talk about that maybe later today. So you expect this deformation lambda corresponds to an irrelevant deformation near the Ising CFT fixed point, meaning that there should be an open window where the phase remains Ising CFT. Right at this point, it becomes a C equals to 710 tricritical Ising CFT.
No, but it seems that even more is true. Not only is it an irrelevant deformation, but it really leaves the critical temperature in there. I mean, because even if it were an irrelevant deformation, you could still expect that that it shifts G a little bit. And something more tricky is going on.
So I'm preserving the non-invertible symmetry, so I stick to the G equals to 1 line. And I turn on this deformation. So I always impose the non-invertible symmetry as I go along this line. And from the CFT point of view, it's clear there's no irrelevant deformation. There's no relevant deformation preserving both symmetries. And that's consistent with the fact that numerically you see there's a region that's this Ising CFT phase. Okay. Yeah, I think it actually corresponds to a TT bar deformation.
Not only that the deformation is irrelevant, but also as you do the RG flow, no relevant term is generated.
That is true, yeah.
Thanks. I did confuse myself.
Okay.
Excuse me, can you remind us what does it mean that the deformation in the CFT that preserves the non-invertible symmetry?
Oh, it just means that I turn on a local operator deformation. I take operator O, integrate it over the entire space, as we usually do to turn on a deformation. And if that operator commutes with the non-invertible symmetry operator, that's what I meant that the operator preserved the non-invertible.
You mean by an operator methodological defect?
Yes. So the statement is that in the Ising conformal field theory, there's no local operator that commutes with the non-invertible topological defect. The deformation is not a topological defect. The deformation is an integral of a local operator. Near this point, this is actually a TT bar deformation. Yeah.
Could you also take lambda to be negative?
Oh, yes. So there's an even more interesting phase diagram. But let me not talk about that. Okay? So then you reach a 710 tricritical point. This is another CFT. This is actually the next minimal model after Ising. And after that point, this phase is gap. The spectrum looks like this. There are 3 low-lying states, and then some order 1 gap. From this phase diagram, it's kind of clear why there are 3 states. It's because up here, you are in a disorder phase, you have 1 state. Down here, you are in the order phase, you have 2 states. So this is just a first order transition between the order and the disorder. And 2 plus 1 give you 3. But if you look at this deformation, it's kind of interesting that as long as you preserve the non-invertible symmetry, the low energy phase is never trivial. It's either some gapless CFT or some gap phase where you have 3 low-lying states. which in the infinite volume limit give you 3 superselection sectors. And this is something you can argue to be true more generally. So in one of my papers, we argue that for every local Hamiltonian that commutes with the non-invertible symmetry D, its low energy phase is either gapless or gap where the number of low-lying states is a multiple of 3. The way we argue it is using gauging the Z2 symmetry. There's a rigorous result by Michael Levine in 2019 where he showed that, he didn't show the 3, but he showed that any Hamiltonian with respecting the non-invertible symmetry, or in other words, that's self-dual, cannot be trivially gap. So this is one applications of the non-invertible symmetry, where the moment you know there's such a non-invertible symmetry, you can say something about the low energy phase.
Which paper is that?
The second, the paper by Michael Levine. Yeah, it's in 2019. It's called Comments on Order and Disorder, something like that. It's a single author paper by Michael Levine.
May I ask a question?
Yeah.
So the critical point has more non-invertible symmetry.
Yes.
Can you realize those from the lattice?
Yeah, that's kind of interesting. I don't think it's there, but I could be wrong. Yeah. There's the Fibonacci, but I don't think the Fibonacci is there. Yeah. And let me also say something that I have to keep track of the time. There's a point here. There's no phase transition there. It's deep in the gap phase. But at this point, I think it's lambda equals to 1. At this point, the ground states of these models are exactly solvable. And I left it as an exercise in the problems. And you can show that at that point, the 3 ground states are plus, 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 0, 0, 0, 1, 1, 1. And the 3 of them are exact ground state. They are exactly degenerate, even in finite volume. You know, typically, you have some exponentially small energy splitting between them in finite volume. But at this very special point, the ground states are exact. And this structure makes it clear that having a non-invertible symmetry is basically telling you that you have order and disorder coexist at the same time. Down here, as I drew it there, down here you have the 0, 0, 0 state and the 1, 1, 1 state. Up there you have the plus, plus, plus state. But along this line, you have all 3 of them at the same time. Yeah, and sorry, let me just write one more thing. So you can show that independent of the Hamiltonian, the way that this D acts on the state is the following. If you act on this disorder state, it gives you a sum of the 2 states. This is typically defined as a GHZ state. So it exchanges the Z2 spontaneous symmetry breaking phase with the disorder phase. Conversely, if you act on 0, 0, 0, it equals to the action on 1, 1, 1, 1, 1, which gives you the plus, plus. So the fact that D acts in the same way on the O spin up and the O spin down state, again, it's a sanity check that D is non-invertible. Because if you act on the difference, they give you a 0. Yeah, there was a question? Yeah.
So the new information from the non-invertible symmetry is that it cannot be trivially gapped. So all the other, whether it is gapless or SSB, is other information.
So it could be either gapless, or it's in a gap phase.
Yeah. So to distinguish these phases, you need other information other than non-invertible symmetries.
Sorry, I didn't catch the last part.
Also, for non-invertible symmetry, you can only exclude the trivially gapped phase. But to further distinguish the details for lambda for g equals to 1, you need other information, other input.
Yeah. It's not determined by the symmetry. Yeah. But the non-invertible symmetry would suggest that the number of states has to be a multiple of 3. in the gap phase. Yeah. And this is also consistent with results that was proven in the continuum, actually in a paper that Fine and I and other collaborators wrote. But here we give a lattice realization. And indeed, as you said, in this gap phase with 3 states, you should think about it as a phase where not just the Z2 is spontaneously broken, but also the non-invertible symmetry is spontaneously broken. In the thermodynamic limit, you will have 3 superselection sectors, O+, O0, and O1. And the Z2 symmetry swapped the O spin up with the O spin down. But now you have a third player in the game, which is the O+ disorder state. And the non-invertible symmetry is also spontaneously broken, and it acts non-trivially on the 3 superselection sectors. Sorry, there was a question. Yeah.
So does that mean there's no non-invertible symmetry SPT?
That's what I'm going to talk about next. Not for this Kramers-Wannier symmetry. Yes, that's a very good question. Yes.
Could you emphasize the fact that it's not activity that's from the anomalies?
Okay, that's a good question. So the answer is probably, but not directly. So the anomaly I was talking about is in the Majorana system, right? That's in a different system. Here we're talking about the Ising model. You can view this constraint as some kind of anomaly for the non-invertible symmetry, but it's a little bit. But it depends a little bit on how you define the anomaly. If you define the anomaly as some obstruction to a trivially gap phase, then this is tautologically true. This is an anomaly. Whether or not it's a consequence of the fact that you have an anomaly in the fermionic system, that's not definitive, because you could have we have other examples where you start with one system with an ordinary anomaly. You gauge some symmetry, it becomes a non-invertible symmetry. But that non-invertible symmetry turns out to be anomaly-free, meaning that it emits SPTs. So the short answer is not directly.
Can you also introduce some notion of order parameter for these non-invertible symmetries to detect SSB?
Right. So it will be some combination, basically x minus ZZ. That will be the order parameter. Yeah.
So when the ground state degeneracy is 3, you can interpret it as SSB. But when it's greater than 3, like 6 or 9, is there an SSB interpretation?
Yeah, so I think typically when that happens, it means that the lattice translation symmetry T is also spontaneously broken. Yeah. Another related comment is that here I presented the lattice algebra for the non-invertible symmetry, but it can flow through infinitely many different fusion categories in the low energy, because T might not be 1 in the low energy. You could have different Hamiltonians where T becomes a Z2 operator, Z3 operator, Z4 operator. And then there are more general symmetry breaking patterns.
Does the statement of non-invertible symmetry not admitting trivially gap phase hold also for non-invertible symmetries that are not obtained by gauging some anomalous symmetry?
Yeah, there could be such examples, but on the lattice it's a little bit hard to construct such examples with an anomaly. Yeah. Let me not make comments. I don't like to make comments about something general. I'm not a mathematician. I'm very bad at proving things. I like to work with one example and try to say something 100% correct about that example. Let me not make a commitment to that.
Yes. Does the 3 ground state imply the spontaneous symmetry breaking of some one-form symmetry?
No, there's no one-form symmetry in the game. Where in 1 plus 1D is too crowded to have a one-form symmetry. Well, you could have, but the model will have, degenerate ground state and all that. Okay. Yeah. Everything is 0 form, if you wish. Okay. All right. So if there's no further questions, we will move on to non-invertible SPTs. Okay. Okay. So we're moving to non-invertible SPT. So if someone hands you a symmetry, it could be either on the lattice or in the continuum. You can go ahead and try to ask, can I realize it, or can it be realized in a trivially gap phase? Okay, so that's a well-defined question. It might be a hard question, and I don't have like a systematic way to answer this question. For some classes of symmetries, I have some techniques via gauging or via some other kind of argument. Generally, I don't. But it's a well-posed question. You can try to prove it one way or another. Now, the answer could be yes or no. So let's separate them. So suppose the answer is no. For some reason, you come up with a proof that the symmetry you are given just cannot be realized it's not compatible with the trivially gap phase. For instance, in Michael Levin's 2019's work, he showed that rigorously for the non-invertible symmetry. Then it leads to constraint on phase diagram, just like the constraints we discussed over there. And you should feel good about yourself, because that means the symmetry is quite useful, and whenever you find such a symmetry, it means something in the low energy. And there could be many such symmetries, right? It could be just an anomalous invertible symmetry. It could also be symmetries involving lattice translation, like the symmetries, like the LSM type constraint. Or it could be for symmetries we just discussed, like the non-invertible Kramers-Wannier symmetry. There's many other examples. Okay, so that's one class of symmetries. And for some community of people, we call this class of symmetry having anomaly. And you can take the definition of anomaly being incompatible with the trivially gap phase. But I'm not going to write the word anomaly on this part of the blackboard. This is what, well, practically I meant. Alternatively, it could be that a symmetry is compatible with the trivially gap phase. This is a much easier case to show. You just have to come up with an example of a trivially gap Hamiltonian, and such that it commutes with your Hamiltonian, with the symmetry. And when that were the case, the question you should ask is no longer the constraints on the phase diagrams. I mean, it still leads to constraints on correlation function, for example. But as far as the phase diagram is concerned, it doesn't lead to interesting constraint. I mean, it's already compatible with the trivially gap phase. But then the question you can ask is, can you classify all the topological phases protected by this very symmetry? And this was the question asked for the invertible symmetry. So for ordinary on-site invertible symmetries, you can go ahead and then classify the SPTs. And for the rest of my lectures, I will talk about the counterpart of this for one particular non-invertible symmetry. In particular, I will argue that the standard cluster state is one such SPT. Okay, so that's kind of the general roadmap. Previously, we are in this we were discussing symmetries like this, and now we are going to talk about a symmetry like this. Okay. But before we talk about non-invertible SPTs, I would like to say a little bit about ordinary SPTs. So I know Max already gave several lectures on that, but here I'm going to focus on one example and approach it from a slightly different angle, but it will turn out to be completely equivalent. But that presentation will help me down the road when I get to the non-invertible SPTs. Any question at this point? Yes.
So just to clarify, you're saying that if you have these symmetries in the example, like non-invertible symmetry or something, then you cannot have a trivial gap phase. And then the yes side tells you that if you like what do the two others mean? Okay. I was just trying to understand what you can say about the ideas. Like if you say, can it be realized in a trivial gap phase, if the symmetry can't be realized, then its basis comes well.
So if the symmetry cannot be realized in a trivially gap phase, that means the symmetry implies something non-trivial in the low energy phase tautologically. Yeah, and you can further ask what kind of constraints you can derive. So for instance, here we will argue that the number of ground states even have to be a multiple of 3s in the case when it's gap. So that was for the first half of the lectures. Now we are going to the yes arrow, where I'm going to present a non-invertible symmetry that is compatible with the trivially gap phase. And now I'm going to classify how many distinct trivially gap phases that we have with respect to this non-invertible symmetry. Yeah. Any other question? Yes.
Is there a more general argument why the Kramers-Wannier symmetry for these trivially gap?
Is there a more general argument?
I saw an example of it here, but if you like
Oh yes, so one argument we presented is using gauging. The idea is that whenever you can prove that whenever the Hamiltonian commutes with the non-invertible Kramers-Wannier symmetry, it is invariant, it's isomorphic to its Z2 gauge version. And gauging a Z2 symmetry will map an order phase to a disorder phase. And the trivially gap phase is a disorder phase. But the disorder phase is not a fixed point under gauging. So you have to have the two, you have to have the coexistence of order and disorder to be invariant under gauging. That's the argument. But that argument relies on the fact that there is no non-trivial SPT for a Z2 symmetry.
So it's not something general for non-invertible symmetries. It's specific for the Kramers-Wannier.
That's right. In fact, I'm going to talk about an example of a non-invertible symmetry that is compatible with the trivially gap phase. Just like for invertible symmetry, some of them are compatible with the trivially gap phase, some others are not.
Thanks.
Yeah. Any other question? Okay, great. So let me start with the discussion. Let's forget about non-invertible symmetry for the remaining of this lecture. Let's just talk about invertible symmetries and talk about the cluster model. Okay. So the setup is again a periodic chain with L qubit. But this time I'm going to assume L to be even. For simplicity, when L is odd, it corresponds to the problem with the defect. Let's not get there. And let's consider two Hamiltonians. The first Hamiltonian, which I'll denote by H product, is simply this. Now, this is a paramagnet. It's as trivial as it can possibly be. And the spectrum looks like this. You have a unique ground state. There's an order 1 gap, and that's it. It's trivially gap. And the state is the O plus states that we have been talking about for a long time. The second Hamiltonian is what I call the H cluster. Takes this form. Okay. It looks slightly more non-trivial, but it's actually not that non-trivial. So let's make a few comments about it. First of all, we have L terms in the Hamiltonian. Every pair of them commute with each other. If the ZXZ are, if the two ZXZ are far separated, of course they commute. But even if they overlap a little bit, like this, you see X and Z pick up a minus sign, this Z and X pick up another minus sign, so they still commute. So it's a Hamiltonian that is the sum of commuting Pauli operators. The Pauli basically means that everything that's made out of products of the Pauli X and Pauli Z. And because you have L commuting Pauli operators, the ground state is very simple to solve. The ground state is just obtained by setting every one of the term to be +1. And since we have each restriction will reduce the subspace by a factor of half. Since you have a 2 to the L dimensional Hilbert space to start with, and you have L such constraints, you have a unique ground state. So the spectrum actually looks exactly the same as the product state. It's just that this time the state is not a O plus state, but it's some non-trivial state, which are called cluster. So even though the two Hamiltonians looks...
You can actually, so since they commute, it means that every state, they can be simultaneously diagonalized. But is it obvious that there exists a state where all of them have eigenvalue 1?
That's the adjective Pauli does here.
Okay,
yeah,
but
so
everything is Pauli.
Huh?
Pauli matrices form.
So one property of the Pauli matrix is that when you diagonalize it, all the eigenvalues are +1 and -1, and you have equal number of +1 and -1. So each restriction from the Pauli projector will cut the Hilbert space by 1/2. So the only thing you have to show is that all these L Paulis are independent. Yeah.
Why are you not writing it if it's so simple?
Hmm?
Why are you not writing the state if it's
I could. Well, it's on the next slide. Oh, okay. I'm getting there. I'm getting there. Okay. Great. Okay, so both Hamiltonians have the same kind of spectrum. And as Slava was already complaining, that there should be a more direct way to see that. So this cluster state can be written in the following way. So this operator, I'll call V. And what is CZ? It's a control Z gate. It depends on two indices. So this is the explicit expression of the cluster state. And you can show very directly that this V operator provides a unitary equivalence between the two Hamiltonians. V is a unitary operator. You conjugate the Hamiltonian of the product state by V, you get the cluster Hamiltonian. So it's not a mystery at all that you have the exact same spectrum, because the two Hamiltonians are unitarily equivalent. Okay, so if you don't care about any symmetries at all, the product state and the cluster states, they are the same trivially gap phase. There's no point in splitting hairs. Okay, but it gets interesting when you try to impose a symmetry. So the symmetry we would like to first impose, and I promise you later on we will impose even more symmetries. But for the moment, we just impose a Z2 cross Z2 symmetry. I'll put a superscript E and O for reasons that will become clear in just 1 second. So the symmetry, the Z2 cross Z2 is generated by these two operators. So I'm taking the product of xj over the even side. And here for eta odd, I'm taking the product of xj over the odd side. That's why I wanted to restrict to L being even.
Is it totally obvious that V is invertible?
Oh, this CZ is invertible. It's a Z, it squares to 1.
Oh, okay.
Yeah, and it's made out of Z's.
Yes.
So it is invertible, yes. Yeah. This V is usually called an entangular. Okay. All right, so in the first part of my lectures, I talk about a single eta, that's the product of all the xj. But now my Hamiltonians will have more symmetries. So I will have two Z2s generated by the xj's on the evens and xj on the odd. And you can check that, you realize the Z2 cross Z2 symmetry linearly. And what do I mean by linearly? I just meant eta even, eta odd equals eta odd, eta even. There's no funny minus sign. And each one of them squares to plus 1. Great. Okay? And you can see that both Hamiltonians, the product and the cluster, are invariant under Z2 even and Z2 odd. Because in the cluster case, whenever you have z's, both z's are, they have to be either both odd or both even. So that's why this Hamiltonian has more symmetries than the Ising model. The claim is that the moment you impose the Z2 even times Z2 odd symmetries, the product and the cluster should now be distinguished. There are two distinct topological phases protected by this Z2 cross Z2. And I will spend the remaining, I'm running out of time. So I will probably talk about that next time. But let me just write a claim here. The claim is that plus and cluster are distinct Z2 even times Z2 odd SPTs. And before I close, let me just comment on the continuum way to think about it. In the continuum, you can think about the difference between these two states as a counterterm. So that's so the counterterm is the continuum language to describe an SPTs, and this counterterm is simply this. So you have a Z2 cross Z2 symmetry. You can introduce discrete Z2 gauge fields, A even and A odd, for the two factors of Z2. I'm not going to use the continuum language that much, but these are background gauge fields. We're not path integrating over them. And this is a cup product, and this gives you some two-dimensional topological action. And the moment you exponentiate it, this is a phase. And that captures exactly the difference between these two SPTs.
There's a missing pi in the exponent? There's a missing pi in the exponent.
There is a missing pi in the exponent. Yes, thank you. All right, so this is an invertible field theory. All right, so next time I will talk about, I will justify this claim. I will present 3 different ways to distinguish the products and the cluster states as Z2 cross Z2 SPTs. And once we have that set up, we will move on to a non-invertible symmetry of the cluster model and discuss different non-invertible SPTs. All right, thank you.